Welcome everyone to our 11th bootcamp session of the SP Europe Energy Geo Hackathon. This is the second version we do this year, and I'm very excited for the session today. We have a special guest, and for those who have already attending our previous bootcamp sessions, you know that this is the 11th bootcamp, and before that we had some theoretical presentations about the application of the problems, and also some practical hands-on sessions on how to deal with the images and how to use Python for image processing. And those sessions will also be continued this week, as you can see, and next week in the program. And if you miss one of these sessions, you know that you can access all the recordings on our Discord channel. So you'll get the link to the YouTube that you can watch the previous sessions. Special thanks to our sponsors, and also different SPE sections and the geothermal technical sections of the SPE who made this possible. And about the session of today, so our special guest today is Patrick Bangert, who is the VP of Artificial Intelligence at Samsung. So Patrick has a very interesting combination of science and consultancy in his background and in different sectors. So he's responsible for the Brightex AI Accelerator, which is a distributed machine learning training and automated ML product, which is focusing on the medical imaging community. And as said, so on the side of the AI science, he's also leading consultancy groups, which is focusing on the custom-made products with the focus on the artificial intelligence for different industrial applications. Before Samsung, he was the CEO at a company called Algorithmica Technologies. And before that, he was also an assistant professor of applied mathematics at the Jacobs University in Germany. He has a background in AI from the University College London. So great to have you here, Patrick. The floor is yours.
Thank you very much. Thank you for having me. Thank you for the kind introduction. Good afternoon, I believe, to most of you. Good morning for myself. I live in California in the United States. Today, I'll be talking to you about data labeling. I won't necessarily give you a demo of such software, but I will talk about what it means. And to begin with, let's talk about the flow of artificial intelligence, the whole workflow from beginning to end, just briefly. There are 5 technical steps, in my opinion. It starts with the acquisition of data, right? You have to get the data in the first place. It could be images, could be time series. You record them somehow. That usually involves sensors being installed in the real world. So definitely in the oil and gas industry, it involves equipment that is installed in the physical world, typically in oil fields, which may or may not be in strange, difficult environments that could get abrasive and hot and cold and perhaps wet. And that step is often called digitization, right? So sometimes there is a confusion that digitization, which refers to that first data acquisition step, might refer to everything. Generally, it doesn't. So once the sensors have been installed in the field and the data arrives in a database, typically the digitization project is complete. And then you have a big celebration by senior level management that digitization is now done. And at many companies in the oil and gas sector, I've seen that to be then it for a long while. So the important thing to understand is that then there are other steps that follow. But of course, digitization or that data acquisition is very important, principally because of the level of financial investment in the hardware that needs to be installed and the amount of effort that it takes to put all of that out there. Then the second step is labeling the data. And that's our topic for today. So this is where human domain knowledge is inserted into that data set in typically a manual process, because it is, well, human domain knowledge. So humans have to insert their knowledge in some manual fashion. And we'll look at a few ways of doing that. So those two steps are the steps where humans are really involved in a major way. And then follow 3 more steps of technicalities. You do feature engineering next. Feature engineering brings out those features of the data that are particularly informative about whatever problem it is that you're trying to solve. So in the case that your data is tabular, it looks like an Excel sheet, it has rows and columns. Every column would be a so-called feature. But you find in practice that many times those features, the raw features, the features you measure in the world, are only somewhat informative about the actual physical situation. What might be a lot more informative is the difference between 2 of those columns, or their ratio. So for example, in the oil and gas industry, often you find the differential pressure across a column or so on to be important. And so it's not the pressure before or the pressure after that are so informative, but what would be great is if you simply subtracted one from the other and thereby had the differential pressure instead. Now that requires several things, right? It requires the knowledge by you, a human being, that the pressure difference is somehow good to know. It requires you to insert that knowledge into the data set in the manner of creating a new column, having it be equal to the difference, calculating those numbers, of course, and then removing the 2 original columns because they're not so important. The difference is what's important. And that consists of feature selection, the right feature to insert, feature generation, the right feature to insert, and then feature selection, which means the right features to remove from that data set. Very important step. Now that also holds true for other types of data, such as images and text. It just gets slightly more complex. In the case of images, since that's our topic today, it's usually an image filter. So we're all used to this when taking selfies to post on Facebook, right? You take selfie, chick, and then you look through the filter for large eyes and, good skin color and like remove wrinkles and things like that. Those are image filters that are being applied to the image to, bring out the right features, right? Okay, it's the same English word. Of course, it means something else, right? Facial features as opposed to data features, but the punchline is the same. You bring out features that you want, and you kind of erase features that you do not want. So that's the same thing in image processing, right? The image that you snap in your microscope, taking that rock slice photo, could be passed through a filter of some kind to enhance the features that you're interested in. Okay, moving on. The next step is to select the right model, right? What model do you want, right? Is it going to be a random forest, a support vector machine, a neural network, a convolutional neural network, or the most famous and modern technology called a transformer, which is the right one to pick. And then what is the right parameters for the algorithm that trains those models, right? Every algorithm has parameters, these so-called hyperparameters. What's the right value for them? Well, unfortunately, in artificial intelligence, choosing the right model and choosing the right hyperparameters is a problem that cannot be solved a priori. There is no deterministic method that you can use to determine the correct answer. except for complete enumeration, unfortunately. So this, by the way, is the holy grail of artificial intelligence. If you solve this problem, you will win the Fields Medal. Generate a method that, without having to do trial and error all the way through, determines the right model and right parameters, right? That would be absolutely awesome. But we are where we are. And doing both of those things is a trial and error process. So you make a choice, you try it out, you make another choice, you try it out, and eventually you basically pick the best one you found. There are ways to make that a little bit less haphazard. They're called grid search, by which you take the hyperparameters and you pick a smallest and a largest value, and then you break up the intermediate space into several pockets, however many pockets you can afford to compute given whatever infrastructure you might have, and then you go through them all. Please don't do that. That is very expensive in terms of computational time. It will take a very long time that you have to wait for it. Not good. The right way to do this is by adaptive search. There are multiple algorithms like this for Python, and in PyTorch, HyperOpt is the algorithm I would recommend. So what it does is it chooses a few points at random, trains your algorithm on them, and then learns from them the structure of that phase space, and then starts to intelligently choose the next points. And so you kind of use AI to create further AI by zooming into the right section of the hyperparameter space. You'll get to the right answer much faster, and you'll end up with a better answer. So if you're going to tune your hyperparameters, please use an adaptive search method like HyperOpt. It'll be better for you. Having done that, you then, of course, actually train the model. By now, that's kind of boring. And now you deploy the model at inference. Inference, of course, is our topical name for actually using the model. This is where you put the model into some sort of an operational envelope of software and services where it actually runs in the field and gets used. Of course, as part of this hackathon, you will not be deploying your model, but the other steps will all be there. Now, having said that, these are the technical steps. I put in vertical at the left and the right-hand side 2 more steps, which are purely human steps. On the left, I say communication. By that, I mean you have to figure out what the problem is. That's very important, that you, who are presumably the data scientist in the project, and the domain experts and the people who manage the project and the financiers who pay for it and the end user that will use your product and so on, all get together and very, very carefully, in great depth of detail, figure out what the problem is and what the solution might look like. If you don't do that, or if you manage not to agree in perfect depth of detail with all these people, then you will likely solve a problem that nobody has. And believe me, this has occurred to me several times in my career, that I've solved problems that nobody ever had, and that the problem that the people actually had didn't get solved. That's bad. So with an investment of just a few days of your time, right, in reality, figure out what the problem was and really be extremely clear on that. Of course, for this hackathon, that's been done for you. But in case you do this again in your professional lives, please don't lose account of that fact, right? So if some manager tells you, hey, go away and solve this problem, take a step back and look at that problem first in a lot of detail. At the very end, we have change management. So oftentimes, and especially in the oil and gas industry, you will encounter a situation where the data scientists have done everything on my chart here, except for the change management. then they will come to the end users and say, hey, I'm paraphrasing, aren't you guys lucky? We invented this fantastic new algorithm. Here it is. Go away and use it. You know, your life will now be way better than before. And then the recipient department is like, hey, we never heard about this. We didn't ask for this. We were not involved in this. This interface looks unusable to me, right? The buttons are all in green. We need them to be in blue, right? So that's the first hint, right? They don't care about the AI that's inside. They care about the visual display of how the thing actually works and looks. They will refuse to use it, and your project will be dead, because you will have invested all this time and effort along the chain, but the only opportunity for you to earn value from your project is if the users use it. And so my suggestion very, very strongly, please involve the end users at the very beginning and throughout the project so that they have an input. They need to have a say in what the problem is at the very beginning. They need to have a say in what the solution looks like throughout the work. And especially they need to have a say on what the user interfaces and so on and so forth look like so that they're practically able to use it. You will find that out of any random 10 AI projects for the industry, the process oil and gas industry, 9 will fail. Not fail technically, not fail mathematically, not fail scientifically in any way, but they will fail economically because the end users, for one reason or another, cannot or don't use that tool. All right, so change management is the step where it typically all goes wrong, because you somehow, or the project somehow, or the users somehow fail to actually retrieve the value. So just be aware. Again, for the hackathon, not relevant, but as you go out there and you do these projects in the corporate world, be aware that will be your obstacle. So I've now talked a lot about this slide, but I feel it's important to know where all this fits in. And then, of course, to emphasize again the work, the human work, the work on you and on the experts is at the beginning. Right, so this is where the financial investment in terms of people hours is, and then the technical steps is typically waiting a lot for the computational infrastructure to do its work. All right, labeling. So we're looking at images that look like this. And now the first thing to do before we can do AI is to label this these types of images. What does that mean? Labeling. Well, you see some structures here on the image that are a bit funny shaped, right? They're not circles or rectangles. So we're going to need to identify these regions, right? And so if I want to say, for instance, that this object here, the little whitish one, is of a certain type, what do I have to do? Well, I'm going to have to draw an outline around it, right? So I might have to use my computer mouse, right? And then click at, click at various points along this trajectory here, carefully isolating the boundary so that I don't accidentally go into this neighboring region or the big gray one over here. And it'll take me some time to click around the boundary and try to be accurate about that. On top of that, of course, unfortunately, I'm not done yet because there are regions inside here, this little black one here, these little black ones in here, which are not the same material as this main whitish material. So I need to have exclusions to that. And I go through the same thing with the region here in the middle and the gray one and so on. You can imagine that it would take me perhaps an hour to draw all these boundaries. And that's in fact what we find to be the case. On average, labeling an image, not just this image, but across the board, every kind of image, right? The city image where you have to isolate cars and people and roads, or medical imaging where you have to isolate different body parts or, cancerous cells. It takes approximately an hour for one person to draw all the segmentation boundaries around the objects in that image. And now you imagine that you have lots and lots of these images. So in this particular data set here, where we have about a couple thousand images, right? So it would take you a couple thousand hours just to label the data set. Now, that's one person, right? But people make mistakes. We find experimentally the average human labeler is right 70% of the time, and 30% of the time has made an error. Now, of course, it depends how accurate you need to be to isolate the exact boundary on the images like this. But nonetheless, 70-30 means that as the organizer of this project, you cannot get away with having a single person label everything. So you need to involve multiple people. So typically we involve 3 people to label everything. And then we kind of take the, best 2 out of 3 for every image. So 2,000 images, 6,000 hours of human labeling, paying for 3 people at least, if not more. You figure out how long 2,000 hours of labeling actually takes in real working time. It's many months. In fact, if you take into account, holidays and sick leave and so on, 2,000 hours on one person is well over 1 year of full-time 40-hour-a-week working time, right? So that's a major labor effort. You can, of course, cut that down by involving more and more people into the process, but we're talking about something pretty intense. What do we do? Well, to again sort of say the problem in a bit more generality, you have to do this with many people. And at the bottom right, you see an example of a modern sweatshop. There is a cottage industry, particularly in countries like India, several African countries, that will label images for you at about $6 an hour, and you can rent as many people as you like. They have literally millions of people. I'm not even exaggerating. Millions of people in full-time work for years and years and years, doing nothing but label images for AI training. So you can do that. For different types of images, like medical images, it gets much more expensive because you need certain domain expertise. And for, of course, this particular data set here with the rock slices, again, you need domain expertise to be able to do that. I could not visually distinguish quartz from anything else. So I would need to be trained. So this is a problem, right? So preparing the data set for this hackathon posed a problem for the organizing committee at the SPE, because they have these images and they're faced with, where do we get 6,000 hours of human labor from? Well, the answer is we don't. How can we solve this problem? Well, the problem can be solved by using artificial intelligence again. So it's again one of those things where it's AI squared. AI is being used in order to create more AI, which I think is really a beautiful thing. The concept that I'm going to talk about here is called active learning. The principal idea here is that out of the entire data set that you have, there is a lot of similarity. In fact, most of the images are so similar to each other that they're effectively duplicates. There are a few images in the data set that are particularly informative, that contain something interesting. And if I labeled those informative images and trained a little proxy model on it, I would be able to label every other image with relatively good accuracy. And therefore, I would then only have to check the labels for those automatically labeled images. Now, of course, those labels won't be perfect, so I might have to adjust them a little bit, but they will be nearly there. And so I will be able to reduce my workload. I won't be able to reduce the workload to nothing because I still have to label that initial few images that make the whole bootstrapping process work. And I will have to correct my labels at the end. But the total amount of labor effort that I put into the entire process will be cut down usually by about 90 to 95%, right? So we were thinking 2,000 images takes about 2,000 hours per person. And now, do it by 3 people or so, 6,000 hours. You can reduce that by 90%, right? So, or 95%, right? So quick mental math, that brings you down from over 1 year to less than a month. Less than a month of full-time work, right? So you're still stuck with some full-time work, but it's not over a year. It's now just a month. And so that's not too bad. That's something you could perhaps actually do. Again, especially if you break it up across several people, right? So it might now be 1 month of work for 10 people, and now it's just a few days for each person, and it becomes realistic, right? So not only does this active learning methodology reduce the amount of human labor effort, it reduces it by enough that things become possible that were just not possible economically or with the amount of people we had before. It's an enabling technology. Okay, so how does it work? Let's go through this diagram real quick to see how this actually functions. So we start, of course, with the unlabeled data at the top left here. This is your data set. Then we perform some unstructured, unsupervised learning, because of course we have no labels at this point yet, which learns the structure of your data set. That structure learning results in a model. That model is effectively a contrastive learning model. If you look into modern computer vision, AI, contrastive learning is very popular. It's basically a method by which you inject the images into a conceptual space by which there is a metric that measures the distance between two images as a distance that is the contrast difference between the two pixel maps in the images. And then you have a distance measure that signifies similarity. What you will find is that in that fictitious space, there will now be clusters, right? Images that are more similar will be a shorter distance from each other, and so they will huddle up in one area. And images that are more different are, of course, a larger distance away, which may form a second cluster over here and a third cluster over there. And so now it becomes fairly obvious what you have to do. You have to pick a couple of images from each of the clusters and get the human user to label those first. So those couple of examples from those clusters form the initial unlabeled batch. Now, a batch is a number of images that is small enough that you can label them in a realistic amount of time, for example, 1 day. So you can go through this in a day. Then that will get you some images that have labels. You could, if you have a model already, in this case we don't, but if we did have a model already, you could apply that to get some pre-labels for those images and present them to the labeling team. Now, this is where the human effort comes in. You now input the labels, getting you a labeled batch. This is now put into the active learning model. The active learning model is an artificial intelligence model. We typically use ResNet 50 as our model engine. This might be helped by another unsupervised model previously trained during previous iterations of this, or during a similar project that you might have done in the past. So with our 2,000 images that we have today, if you ever acquire another 2,000 images, then you would use the model you generate in this project as the unsupervised model of the future project. You now apply this model to the remaining unlabeled data, and you evaluate what we call an acquisition function. An acquisition function is the function that decides which images to acquire from the unlabeled batch in order to generate the next batch of labeling. Right? So the acquisition function is supposed to determine which images are most likely to be very informative, which have the highest probability of offering useful information for the process. Now, this is where our main innovation at Samsung has come in. We've invented a novel way to do this by Bayesian probability theory. It's fairly sophisticated, so I won't go into the mathematics of it. But it's the acquisition function where the secret sauce lies to do active learning properly. The bottom line is that it extracts or acquires from the pool of unlabeled data those data points, or images in this case, that will be labeled next. So they form a second unlabeled batch, which are labeled by the people. And you see this as a loop. You go through the loop, and at every execution of this loop, we, of course, assess the accuracy of the active learning model. How good is that model becoming? Is it good enough? Then we stop the cycle. If it's not good enough, of course, we go back to the cycle and we continue. If it is good enough, we exit the cycle. We have the active learning model, of course, already. We apply it, and then we get a fully labeled data set. Most of those data points, however, are, of course, automatically labeled, which means we can't just accept them. We have to review them. So there's a reviewing team involved that now looks at those labels and checks them. At the other end, we have an image that has either been labeled by a person, an automatically labeled image that has been checked and verified by a person, or an automatically labeled image that has been corrected by a person. Right, so every single image has nonetheless been seen and certified by a domain expert, but using much less effort. Right, so the point is reduction of effort. That ultimately can then be fed into the actual AI. Right, all of this up to this point right here is just helping label data. Now you can do the actual artificial intelligence, resulting in the actual model that you wanted all along. Right. Everything else here, just a helper. Now, this looks complicated, and it is. To actually make it work in a real-world software program, you need to use several technologies that already exist, and we use these ones on the right here to put together into making an environment that actually executes on all these concepts. So you can tell that, of course, we stand on the shoulders of giants, just like everybody else in this field does, and we build up on that. And so in your project, of course, you will also be using multiple previously existing technologies to get your work done. Now, this active learning approach is very useful if you want to cut down on the amount of work that you need to do in that data labeling preparation stage. So I do suggest that you use it. There are tools available. The tool we made at Samsung is one of them, but it is certainly not the only one. You will find others. And the organizing committee for this hackathon is currently going through that process. So thank you and kudos to you for doing all of that work. And you, the hackathon participants, will of course be the beneficiaries of that. Having done that, in the end, we of course need to consider what to do in reality. And this is where data labeling kind of makes a comeback. When you have your AI system that you deploy in the field, you need to make it operational for the domain experts, of course, right? They're not going to do AI. They just want to use your AI system, which means you need to offer it in such a way that they're able to do that, which will typically involve integrating it with the data systems that are already in place. So in the oil and gas industry, that could be process control systems or laboratory data systems. It could be going as far as the SAP system that interacts with the finances of the company. So there need to be interfaces put in place that use all of this. I've talked about change management already. You need to convince the users to actually use it, which often can be challenging. The most important for our labeling aspect is that you have to manage the model in production. What does that mean? The key phrase here is model drift. Now, of course, models are a mathematical formula after they're done, right? They're static. They don't change. So why do people talk about model drift? Well, it's really a misnomer. It's not the model that does the drifting. It's the world that does the drifting, or the data that does the drifting. Because as you apply your model in the real world, more and more data is coming in, right? New data points coming in, I apply the model, give an output. New data point comes in, I do the math, provide an output. So as the new data comes in, my data set grows, right? At the moment, I have 2,000 images, 2001, 2002, 2003. My data set grows and grows. However, those new data points are not labeled. They become labeled through my model as I provide the output, right? My model output is effectively the label, but it's not a real label. It's a synthetically computer-generated label. No human being has certified that this label is correct. Well, that's problematic. It's problematic for the reason that almost certainly the distribution of the images that you trained your model on is different from the distribution that you find in real life. Because for one reason or another, things change, right? You're now drilling in a new reservoir or a new area, or you're drilling deeper, or you're drilling horizontally, or you encounter a new rock formation, what have you. The distribution of the data you encounter in the real world is different from the distribution you trained your model on. And so it's the data that drifts. It's the world that drifts. Now, you will never see it unless you manually, by human expertise, look at least some of the data that's coming in and enlarging your data set over time. So that phrase is called model observability or model observation. Models need to be observed as they're being applied, which means a continuous stream of labels that have to be injected, right? So what happens? Data comes in, model is applied, an auto label is sent out. A human expert looks at that label and says, either this is good to go, or I need to correct this a little bit, and then it's good to go. And of course, you have to save all those corrections so that in a little while, when you're discovering, okay, my model used to be 99% accurate, then it was 95% accurate, now it's only 90% accurate. At some point, we need to retrain the model to make it better, to bring it back up to 99%. Well, retraining the model only makes sense if you have novel data to show it, which of course you've collected in the meantime. Otherwise, you would have never been able to assess that your model has in fact become less accurate over time, right? So again, I'm just reminding you that labeling is an activity that is a continuous activity over the lifetime of the use of that model. It is not a singular activity that you perform at the very beginning and then you're done. You're not done. It has to continue and be embedded in the use of the model over its lifetime. And so labeling is part of deployment, right? So this is one of those misconceptions that people have, that AI training is done and finished at some point, but unfortunately it has to continuously take place, and that has, of course, ramifications on the financial investment of making such things happen.
Patrick, there is one question, if I may interrupt, because it was mainly about the similarities or the differences of the active learning workflow that you have shown to the self-supervised learning algorithm. So the question is that, are these similar or different? And if different, what are the differences?
Right. That's a very good point. Self-supervised or unsupervised or semi-supervised methodologies are largely based on the algorithm learning itself from the structure of the data set. In the diagram I showed, those methods would be up here. These are the unsupervised methods that learn the structure of a data set based on the data set alone. Everything else here, this entire loop here, and the idea of active learning involves necessarily and essentially people, these guys here, the labeling team. And so it involves the injection of human knowledge through performing labeling on a select few data points, right? So that's really the important difference. Unsupervised learning, self-supervised learning does not involve humans that label. And so the outcome is kind of by definition going to be less accurate, right? You're putting in less information, and therefore you will get less performance out of the process. Of course, self-supervised is fantastic if it's good enough for your purpose, because you don't need to rely on a human labeling team, and therefore it's much cheaper and much less annoying. So the real question for you, if you're going to consider methods like this, the real key question is this one right here: good enough. You have to define an answer for good enough, and that answer is a number, right? It's not a feeling. The answer good enough is, what is the accuracy of your model that solves the problem? In some cases, 60% accuracy could solve the problem. In some cases, 90%, right? In some cases, 99%. That is up to whatever problem you're solving. How accurate do you need to be to solve the business problem? That is up to you to decide. And based on that, by all means, try out self-supervised learning. See if you hit the required accuracy. If you do, fantastic, celebrations, you're done. If not, then you're here, right? And now you can start this process to get yourself a higher accuracy. So if there are no more questions at this point, I'll go on just briefly to mention a few associated issues. There are, of course, always data governance and privacy regulations in case you ever do collect data that is connected to people. Oftentimes we inadvertently collect data relevant to people, such as who took the image, or in some cases who is on the image, who is responsible, and so on. In Europe, you have GDPR regulations. In the United States, we have HIPAA regulations. In different countries, you have other regulations. So this is the other difficulty, that in an international environment, working for a multinational corporation, you may find yourself having to obey multiple governance strategies at the same time. They may even be somewhat in conflict with each other, and you need to manage that, of course, in your data system. Labeling is particularly interesting in that regard because, of course, it's humans that label, right? And so as you're labeling, you are by definition collecting privacy relevant information on what those labeling people did, when they worked, how good they worked, what their accuracy is, what their speed is. And now, if, for example, you're proposing to restructure, let's say, your labeling team by removing the people who are less accurate or less efficient, suddenly you would have a GDPR problem. So I'm just mentioning that in passing, so that you can think about that when you put your labeling infrastructure or your labeling software in place, that almost by necessity you will hit the governance problem, at least with regards to your personal information, if not the data itself. Of course, here we're dealing with rock images, so data privacy doesn't come into it. But if you did do an autonomous driving use case with street scenes, you would have people on those images, and then you would have privacy related to the people on the pictures themselves, and that gives rise to other sorts of regulatory issues. So let me come to the end and say the takeaway lessons from this is, first of all, in my mind, AI is the upcoming future, or the upcoming frontier. Definitely in the oil and gas industry, we figured out how to extract the oil and the gas from the ground a long time ago. Now it's time really to do that more efficiently, and get everything out. And artificial intelligence has been tremendously effective in that. When you went to the SPE conferences just maybe 10 years ago, or even maybe 7 years ago, you will have found that the number of AI machine learning papers that are presented at these conferences would have been 0, maybe 1 or 2, and that would have been me. Nowadays, if you go to an average SPE conference, you will find that at least a third, if not more, of the papers are AI relevant. So I was at the big conference in Saudi in February this year, and we counted 45% of all the scientific papers presented there were somehow using AI or ML. So that's a tremendous uptick from years ago. Now, of course, we're not quite there yet in terms of applying AI in the oil and gas industry. Most of those papers are research papers, studies that are isolated, but it's coming. C-level in the oil and gas industry is investing into AI. More and more projects are being actually implemented in real life. They're being used. And so it is still a frontier. It's not quite a ubiquitous technology as it is for us as private people. Of course, in the home, AI is used all the time, right? Who decides what Netflix movie you watch or what Amazon product you buy? It's AI. Who decides how much your airplane ticket costs? It's AI, and so on and so forth. But in oil and gas, it's still a frontier, but it is the frontier. Data annotation or labeling, as we've discussed during the talk, is really the central obstacle. It's the central obstacle based on the human time it takes and on the financial investment that you have to put into it. The actual mathematics of artificial intelligence is the small part. So data preparation is most of AI. It's the labeling, it's the cleansing, it's the removing of irrelevant data points, it is the filling of holes, that have occurred because your field infrastructure wigged out on you. It's teasing out the right features, deleting the wrong features, picking the right models. All of that is the data preparation so that you can do proper AI. And that really is most of it. Even though in the scientific literature, if you look at books and papers on AI, most of it, I would say maybe even 90% of the literature on AI is regarding algorithms and models and mathematics. Most of the actual practical AI in real life is data prep. Right? So this is another message to everybody out there who might be getting into this for the first time. This is where disillusionment hits many people, especially who come from university, who want to work on algorithms all the time. The actual real life work in AI is mostly data preparation. Now, in this case, in this hackathon, of course, the beautiful message is that the dear people who organized it for you did all of it. So you get to indeed just do the real fancy AI and invent the new algorithms. And I'm very excited to eventually hear and read which team did the best job and to learn what algorithms you chose, what methods you chose to prepare the data properly for this analysis. I'm very excited to find out. I think this is an extremely useful case and a very good study. And I salute all of you for donating your time and participating. Thank you very much. And if there's any questions, I can go through them now, or you can connect to me on LinkedIn and we'll talk about them later. Thank you.
Patrick, thanks a lot. Great presentation. Really interesting. So I see also some questions are popping up. I will see how much we could do in view of time. So I'll start with the first question from Adam. And the question is, yeah, eventually if we want to assess our models, we need to have some sort of, let's say, a ground truth to know what sort of accuracy do we make in our models. So how can we actually measure it in this case, if there is actually no ground truth in the data sets? And then he also has a follow-up question which says, if eventually we have some, let's say, existing models which can represent that ground truth, and we compare our models with that, let's say, existing model, then why do we need to create a new AI model at all? So that's a bit of, let's say, gist of the question. But I think the most important thing is that if there is no ground truth in this case, how can we measure the accuracy of the model?
Right. So that's a really good question. If there is no ground truth, then you cannot measure a model accuracy. Right? It's as simple as that. Now, ground truth is just another name for labels, though, right? So labels, annotations, ground truth, that's the same thing. So what you need to do in this particular hackathon case, as well as in every other case, is you need to divide your data set into two pieces, into a training piece and a testing piece. And you use the training part of the data set to do everything that I went through in the workflow, to generate the features, to select the features, to select the model, to tune the hyperparameters, to train the model, everything you do with the training part of the data set. The testing part of the data set, you do nothing with until at the very end, you're ready to assess the accuracy of your model. And then you apply the model to the testing raw data, compare your model outputs with the ground truth, the labels of the testing data. And that's when you assess your accuracy. And that's really the only way of doing it. That's why every literature goes through that division. You could do it multiple times, in which case you would divide the entire data set into, let's say, 5 or 10 buckets. And then you go through by saying, okay, bucket number 1 is testing, then bucket number 2 is testing, right? That's going through multiple folds of the process by which you get a much more rigorous assessment of how accurate you are, but you require ground truth. And the ground truth are the labels, and they're being provided to you.
Great. Thanks. The next question by Ryan is, how do we tackle the imbalanced data resulting from our being labeled data? And the follow-up question is that if the method that you have shown and proposed is actually working efficiently with this imbalanced data problem, and if there are some information about this methodology that can be shared. I assume if it's not being IPs, if it's not your IP, probably that's going to be easier to share. But yeah, the floor is yours.
Yeah, no, excellent question. Thank you. That's a very, very important point, actually. So imbalanced data for everybody means that I have more images of one particular category and less images of another category, right? So I might have 70% of my data being in this realm of space and only 30% being over here. So if a model is quote unquote fair, I'm going to be accurate over here and inaccurate over there. And that's of course bad. So how do we deal with this? We need to undersample the part that we have lots of data on, and we need to oversample the part that we have little data on. Now, if you as a human AI engineer know about this problem in advance, you can, of course, engineer that selection again by demand, right? You can enforce that kind of sampling. Now, if you don't know that in advance, or you don't know where the categories are, you don't know how many images are in each, then you will have to rely on an AI system to do it for you. And again, AI squared, right? Use AI to help you create more AI. Active learning is a beautiful example of that. This methodology that I showed you via that acquisition function, which identifies the images that are most informative at every loop of that process, does exactly that. It does stratified sampling for the distribution that you actually have. So it will oversample the less represented categories, and it will undersample the more represented categories by definition, without you, the AI engineer, having to explicitly encode that in any way. And yes, this research, by the way, is not proprietary. It's published. You can read about it in multiple publications. If you go on archive.org, that is arxiv.org, and just put in my name as author, you will see multiple papers on these technologies if you're interested in learning more technical details.
Brilliant. That was also a question I had, which was about going from this acquisition function to the new batch. So you already addressed this imbalance problem, how you can deal with that. And I was also wondering if also something in the structure of the data. So if, for instance, one is more towards a certain, let's say, structure, or let's say some attributes are being shared and some are very, very far from this, do you also do something in terms of sampling from those data? But I think that we already answered this. So it really depends on, let's say, on this also imbalance problem, that you try to kind of make a fair sampling between the all the different, let's say, features or the structure that you have in the data. So I think that's that's very well covered. I think in view of time, this will be the last question we're taking. Thank you for your nice talk, and of course, it's not the only one. There are several people thanking for the lovely talk. What's your view on using deterministic methods versus AI methods, given the generalization issue of artificial intelligence when you apply it to new data?
Wow. Okay.
Yeah. This is a separate talk.
We can spend a long time talking about this. Now, of course, I head up the AI division at Samsung, and so I'm biased. All right. So that first of all, but I did start out taking a physics degree back at college, and so I'm familiar with the dichotomy between data-driven methods and deterministic methods. And I will say this: if you know the situation perfectly well and you're able to encode it in, let's say, partial differential equations or logical reasonings and so on, to the degree that it will actually solve the problem, then I would say deterministic methods always win. And so again, if you're able to use deterministic methods, my opinion is that they typically are better. Better in a scientific sense, in the sense that they will be more accurate, they will be more reliable, they will be more understandable. Two caveats to that, though. The first is the economic caveat. Using deterministic methods is often, not always, certainly not always, but often more expensive in terms of the amount of human time required to put them together, in terms of computational time and computational infrastructure to execute on them. Many simulations solving partial differential equations can be extremely time consuming. The second caveat is most of the time that I have ever tried this, and I know many colleagues in the same boat, we simply did not understand the physical situation at a deep enough level to be able to encode the situation in the usual physics language or deterministic language, the logical language that would allow a sufficiently accurate simulation. So take just a case in point, the formation of quartz crystals in geological formations that we're solving here, right? If you were to put this into a simulation, right, you would have to simulate the formation of, microscopic crystal structure in a macroscopic environment, difficult, over a time frame of, a very long time frame, millions of years that it took to form this thing, difficult. You would have to get enough resolution. You would have to customize it to particular geographies in the world that have access to certain amounts of base material to form these things. This is information that I don't think you have, and you might not even be able to get, even with lots of trying. So you're looking at using deterministic methods on an ill-defined problem, missing information, and possibly using, I don't know, hundreds of man years of computation time to get it done. I think you're looking at an unsolvable problem from a deterministic point of view. Now, data-driven may not be perfect. We may not understand it completely well. It's a black box, and that's not great. But it'll solve the problem to a certain extent, and it'll do it in a realistic time frame. So sorry for the long answer. We could talk about this for a long time, but again, if you're able to apply deterministic, please do so. In this problem and many others, I don't think we're able to.
Thank you very much. So I think with this, we would conclude this bootcamp session. Once again, thanks, Patrick, for a very interesting and informative talk. And thanks for the audience who stayed with us. And we will see you tomorrow again with our next bootcamp, which is about another tool by NVIDIA about the computer vision. So see you tomorrow.
Thank you very much. Have a great day. Bye.